Hi everyone, and welcome to Sweet Streams Are Made of These, data and metrics-driven development for stream processing. My name is Caito Scherr, and I'm a developer advocate. I represent the US region for Vivarica, formerly known as Data Artisans, the creators of Apache Flink. I'm based in Portland, Oregon, and I used to be a software engineer at a data analytics company. And I've been working with stream processing with Flink since 2017. So combining metrics and stream processing is something that I could geek out about for hours. It was very hard to cut this talk down to under 30 minutes. And that's what I'm here to talk to you about. Using data and metrics driven development with stream processing, including which tactics should be modified or really prioritized for stream processing. So data-driven development can mean a lot of different things. So I'm going to start with some basic principles that I'll be covering in this talk, as well as briefly a few fundamental concepts about stream processing for any of you that may be unfamiliar. Next, where to even get started. So how do you know what to measure, what's going to be the most helpful to you, and how do you figure that out without spending a lot of time and energy on it? I jokingly, but also seriously, like to think of this as metrics-driven metrics. And that's going to be kind of the bulk of this story today. Lastly, stream processing has some additional challenges in how it impacts the surrounding ecosystem that are just kind of unavoidable. So this part's going to be fairly short, but I think it's important to end with some metrics about where those integration points come into play and using metrics as a shared language to minimize some of those challenges. So briefly going over some of those basics. If you Google the title of my talk, maybe not the pun version, but the subtitle, you probably notice that there's a lot of terms, a lot of different interpretations and opinions on each of those terms. And if you search specifically for data-driven development, you'll most likely find information about business metrics and data-driven design. And there's actually a pretty big overlap between those two, as essentially the main focus there is using data to drive the design of a product that customers actually want to buy and use. So it's important to note the differences between the two though, because that's going to really change how you use your metrics and who's actually going to be using those metrics internally. Business metrics refers to anything related to internally measured success. So team velocity, sprint burn down, lead time, those sorts of things. Business metrics can also include what some people refer to as vanity metrics. Vanity metrics often include things like, we're putting out 3 million messages through a day. Things that are very impressive, that look really good for press releases and blog posts. Data-driven design relates specifically to the end user experience. As the name implies, the main focus here is to use data, typically data involving usage patterns and user feedback, in order to better understand and design for the needs of that user. Data-driven development is often kind of lumped together with these two or used as an umbrella term. I do think it can still be appropriate as an umbrella term, but my focus in this talk is where it represents metrics that are targeted at changing the development process itself. So that's what I want to talk to you about today, because I think it's just really essential to be able to look at that on its own in order to really leverage it properly. Secondly, there's a set of principles that come more directly from data-driven design, but they're relevant in all of these areas. It's this idea of a three-tiered approach that defines the type of metrics you use and how they guide your product, but categorized by their relationship with quantitative or qualitative data. Data-driven design is centered purely around quantitative data. This process is applicable to aspects of the software design like optimization and performance. As you progress outwards, you next have data-informed design, which weighs and utilizes qualitative and quantitative data equally and usually together in order to make a design decision. Furthest out is data-aware design, which is typically focused more on directly qualitative information, but quantitative analysis is often still used as a base or to pair with customer use stories, detailed feedback, or discussion-based risk-reward analysis. This category is often thought of as one that takes the larger picture into account, which is why this diagram is often portrayed more like a circle like this. So I like using both of these, but the value in this one specifically is that it really shows that wider scope where it takes progressively more types of data into account. It's also important to say, because this will come up later, that typically development styles in the center tend to be much easier to automate, whereas the further you go outwards, the more and more manual those processes will likely have to be. This is also particularly relevant for how to share metrics effectively with different internal teams and groups as you get closer or further from the engineering team that's at the center of that project. Lastly, very short review of stream processing. So a lot of you are probably familiar with stream processing, so I will try to go through that pretty fast. Okay, so as the name implies, stream processing involves a continuous stream of data. This is used primarily as a distinction from batch processing, where data is published as a system to a system or application in bounded units or batches. With a continuous stream of data, there's a lot of benefits. Most data is actually already best collected this way, whether it's input from a video game, weather sensor readings, or customer usage patterns. And without breaks or having to wait for new batches, it naturally has more potential for faster data transfer and processing, having much lower latency. And with most stream processing frameworks, you can ingest data from a variety of sources, which produce the events, like these on the left here. I think that should be the left. And at the very end, most frameworks also allow you to publish data to different varieties of sinks, like a data store, various types of storage, or even to another data stream, like any of these here on the right. And in between is the fun part. So typically, data from one or multiple of these sources is written either to a log, to another data stream, or to a message queue like a Kafka or Pulsar topic. Then you have your actual stream processing application, using a framework like Apache Flink, Spark, Storm, etc. And as you can see, some stream processing frameworks are paired with local or occasionally external storage that enables the current application state to be stored regularly, similar to like a snapshotting system. This is referred to as stateful stream processing. This looks a little different depending on which framework you're using. So Spark, for instance, distributes the state onto a cluster and does most of the management there. SAMSA replicates state across multiple machines. Generally though, and on a high level, being stateful means better fault tolerance as it can be used for updates or rollbacks in case of issues or outages. It can also be used for A/B testing and working in parallel with different versions. In Flink, they use checkpoints, which are a mechanism that copies the current state of each task after all the tasks have processed the same input. So in case of an outage or other kill processes, there are mechanisms that restart the whole app, and then before the tasks are started again, they're going to be reset to that last completed checkpoint. Frameworks like Flink also allow for querying on that application state, which is pretty cool. Okay, so now you're all stream processing experts. Awesome. All right, so we covered event producers or sources. We covered the queue, which is the log or initial data stream. We also covered the actual streaming application. And then of course the sink, where the data is eventually served up or published to. Awesome. Okay, so now the challenges of a system like this are that you're now ingesting unbounded streams of data, and you're regularly storing the state, if it's a stateful stream processing framework, of an application that is continuously consuming possibly massive amounts of data. And it never stops. At least you really hope it doesn't. It shouldn't. So all the benefits of stream processing, being able to push through huge amounts of data and super fast, all of these have what are probably some fairly obvious impacts on anything that's going to be downstream of your application or anything that's related to storage along that stream. Additionally, you could have a streaming application that consumes data directly from an initial source, but it's much more likely that the data you're consuming has already undergone several different transformations. It's also likely that your application is consuming from multiple different data streams, possibly even having to merge them. This means that you could be consuming data in multiple different formats, or possibly even have very different throughput rates coming in. It's also likely that your application is going to need to publish data out to multiple different sinks. This is actually extremely common, a very common stream processing scenario. However, full coordination with upstream and downstream teams, particularly in relation to metrics, is often overlooked. So overall here, the biggest challenge that I find with this type of architecture is that the relationship between an application in this situation and its technical ecosystem around it changes so drastically when that becomes a streaming application. So integration points become much more complex, which I'll be going into later, and structuring your metrics around those points and being able to keep those metrics meaningful without a lot of hassle, and when multiple different groups and teams might be sharing any one integration point. So that's what I really want to get into here. On a separate note, I think it's really important for systems to be provider agnostic, even when it comes to metrics. So because, if the product that logs, tracks, analyzes, and alerts on your data goes down, it would be really nice to have a backup for that too. So this could be as simple as maybe just having a JSON API that you can query as part of your system. So if the worst happens, you have redundancy for your logging and monitoring as well. For this reason, I'm going to try to keep myself provider agnostic in this talk as well, so you will see metrics from various different monitoring and alerting providers here. Okay, so metrics-driven metrics. How do you know what to measure to know what to start measuring? I know, right? And how do you get started, and how do you know what those right metrics are, especially if they change? Okay, so first though, you really do have to start somewhere, and often the best start is something really simple like measuring as much as you can for proof of concept or playground application, getting as close to production as possible, or even just a steel thread that just has those highest valuable features and behaviors. Starting that as a small cycle, growing it with the growth of your application's development. Great. So in addition, whichever framework that you choose is going to have its own recommendations for specific key components to measure. However, within this, it's really easy to get lulled into measuring just what's recommended, which is where data-driven development comes in. So later I'm going to have some examples of that specifically, where this metrics-driven metric cycle has really drastically altered how we measure that initial list of components. In the meantime, this is a really great example of a pretty full list of which Flink metrics to start with, most of which have direct equivalents in other frameworks. I'm using this dashboard as my example here because this provider does such a really great job at explicitly labeling what's important to track in stream processing, and specifically Flink. Like, I actually literally wrote down a list, and then I found this image and I was like, oh, that's exactly what I have, which is great. I love when that happens. So firstly, Flink actually has a UI that includes pretty much all this information here with a couple additional things as well, including how many jobs are running, restarts, task manager count, etc. So on a high level, these represent most of the key components that actually keep Flink running. So if you're using another stream processing framework, you want to make sure that that's on your list, that you're tracking the equivalent of your running jobs. Very important. And one thing that I also really like about this dashboard is that you can see several different, completely different complementary pieces of your checkpointing all in one place. So failed checkpoints as a single number is useful, but combining that with the last checkpoint completion over time and over a span of a couple different hours, that combination is way more impactful. So I really like to show this in particular. So resource utilization, seen here in this column on the right, this is particularly useful for Flink as a lot of the operations are dependent on the JVM heap. However, resource management for any stream processing framework is going to be very important because of that higher impact that a memory leak could have when you're continuously streaming in data. And I'll cover some of the rest of these metrics, like throughput, for instance, later on. Okay, so beyond all of those specific components that you can grab, you can measure those right from the start. When it comes to knowing where to start and what metrics are going to actually be valuable to you, I found that trying to have one single answer to these questions is just not very effective. Instead, I was much more successful when I framed this as a process, so an ongoing iterative practice of knowing your normal. The main components of this practice are super simple: focusing on what's meaningful, staying iterative, and keeping it accessible. As for keeping your metrics meaningful, starting with some good basic dashboard hygiene goes a surprisingly long way in enabling a process that will help you keep your metrics meaningful. Firstly, your dashboard should reflect the values and development priorities for the application that you're monitoring. This sounds obvious and sort of generic, but I want to emphasize that just how important this was for us on my last engineering teams for stream processing. With our non-streaming applications, we could sort of loosely adhere to this philosophy, and it just really didn't matter. But with stream processing, because of those extra complications, that extra impact, we found that this was much more essential for a variety of reasons. For instance, on an engineering team that I was on at another company, this was actually an example of the top of our main dashboard. And I love this one too. It's a great example of one that was really curated to have those metrics right on top that are actually going to be the most important to engineers and that are really the ones that are most driving that development process. There were more metrics below, but this is just the top half of the dashboard, and we were very selective about what went in that top half. Although we're also flexible. If the top engineering priorities changed, so did the dashboard, which usually just meant swapping out one chart for another that was already further down on the list. For this particular one, the stream processing Flink application, the consumption from our Kafka topics and our watermarks were particularly valuable, so you're going to see that at the very top. So watermarks in Flink, as with some other frameworks like Apache Spark, are a mechanism for controlling the duration of time that the application will wait for a record to arrive. This feature has many applications and is the basis for most event time operators. Watermarks often help determine how late records are handled, meaning it can have an impact on whether, what order, and how data is ingested into a stream. So it's important, but it's also something that's usually an estimated guess, designed by or designated by the engineer. So this is why it's really essential for us, at least in that early development of the application, to keep a really close eye on those watermarks, because this was a configuration that we were probably going to have to adjust a lot as we got more and more information about the data coming through. So a really good example of getting that metrics-driven metric cycle going. Next, each of our incoming data streams had its own lag chart. By taking some initial measurements of data flow, and analyzing how data was aggregated and the structure of that output, we were able to determine that some of our upstream teams aggregated and transformed their data completely differently than what we had expected, and that it even differed by team. So it was super valuable for us to place the metrics here for each team into groups based on how that data was aggregated. So just separating those out and really having that structure. So how this helped drive our development, though, was that once these metrics were in place and we had a better understanding of just how differently data was handled between different upstream teams, it naturally guided a restructuring of ownership. This information almost automatically redefined responsibility for integration points in a way that was based on the behavior of the software itself, which was much more efficient than how it had been structured previously. So next we have throughput and checkpoint size, which is our next priority. Throughput hopefully is an obvious one. You really want to have a good handle on how much data is going through your stream. We had our throughput separated out by which source the data originated from, which enabled us to have an overall view of the throughput throughout the whole system, but it also allowed us to click into a specific upstream application when needed. We also tracked throughputs at each reduce function throughout the streaming application, which I highly recommend. As I mentioned earlier, checkpoints, or in general, for any stateful stream processing application, anything that's related to how your state is stored, this impacts so many essential parts of your streaming application, so it should be fairly clear that your engineering team should be fairly familiar with what's going to be normal and abnormal for those components. So this dashboard, however, actually has a very unusual way of tracking checkpoints, which brings us to keeping this process iterative. So it's much more common in Flink to track the number of checkpoints, usually for a certain duration like the last hour, or for any anomalies over a longer period of time like a day. However, for our team here, at this point in the application's development, we are under certain restrictions for how we wrote our data to the sinks, and some sinks still needed to consume on a once daily cadence, almost like a batch. So for this, we focused on the checkpoint size, which should follow a predictable pattern of steady growth and a single once daily drop for the situation. In this case, an abnormal drop or spike could mean that we were losing state, or in one case that there was a mismatch in how incoming data from different sources was being timestamped, which was a whole very interesting thing. So overall, instead of being completely stuck on textbook metrics, which is a great place to start, it was much more effective for us to stay flexible. It was important to allow the data that we were receiving about our system, along with any other information that we had in our weird and unique system, and really trying to be data informed here, to guide modifications to our metrics, keep that cycle going, and even if that meant monitoring in very non-traditional ways. Okay, so you have a dashboard that has meaningful, prioritized metrics and supports iteration and flexibility, right? Yeah, yep, check, awesome. Okay, but they have to be something that's easy to use, especially if you get paged at 3 in the morning and you need to make sense of all those pretty lines and colors. So there's a lot of different techniques for this, but honestly, the most helpful thing that I've found in thinking about this is scale. Because having the right things in the right order will definitely help with easy use, but prioritizing a list of 1,000 items is still 1,000 items, and especially with stream processing, that list can get long very fast. So this brings us to accessibility and the actual practice part of that metrics-driven development. There are tons of resources, I was going to say a metric ton, Sorry. And also tech blogs, etc., about how to be intentional with what to measure and why, and where you put it. So a couple of my favorite quotes on this are, one of them was a Harvard Business Review saying, "It is simple enough to describe how to inject data into a decision-making process. It is far harder to make this normal, even automatic, for employees. A shift in mindset that presents a daunting challenge." Or more simply, a Tech Beacon article reminding us that you can measure almost anything, but you cannot pay attention to everything, which is a very hard lesson for me because I do want to measure all the things. However, my favorite quote was actually from another engineer that I was talking to recently about this, who said that any situation where people create their own dashboards without structure quickly starts to look like the cockpit of a 747. And I love this because it gives you such a great image of what this anti-pattern really looks like. And unfortunately, I'm guessing that we've probably all seen dashboards that look like this at one job or another. So I just really want to emphasize this is just a nope, just nope, nope, nope. So yeah, and with that, now we can move on to metrics as a shared language. So there's another great Harvard Business Review article that mentions that the biggest obstacles to creating data-based businesses are not technical, but cultural. More specifically, I like to think of it as that even the best data-driven development fails easily when it's only built for yourself. This fact is something that we could still basically ignore on most of the teams that I was on for all of our non-streaming applications. But as I've been mentioning with stream processing, those integration points are so much more complicated that you're likely to have much, much different relationship with those upstream and downstream applications and teams. So I feel like this is just really important to cover. When we built our first streaming app system at my last company, we found that people from all over the company suddenly needed a lot more information. Explaining the same stream processing and Flink concepts, re-explaining our streaming specific alerts, being included in incident resolutions that seemed maybe kind of far from our domain, all of these suddenly became part of our development process. Some groups, like other engineering teams, needed the same granularity as us, but filtered a little bit differently. Other groups needed to be able to pivot between summaries and depth, and still other groups needed full abstraction. And I like to use this diagram because it delineates these groups, but it also has the group in the center that needs the most in-depth technical coverage, and then the further you get out, the metrics and the way of sharing them become much more and more abstracted, similar to that data-driven and data-aware circle from the intro. But it's really easy to forget that metrics are a powerful tool for communicating quickly and accurately across these different audiences, and is a really great way to help really, really minimize some of these issues and make them almost non-existent. So starting from the center, monitoring for yourself. I gotta say, this is probably the monitoring that we think about the most, let's be honest, and this may be the only monitoring that we think about. So I'm not gonna really get into this one because we've actually covered most of it already. So specifically, that was about where to start, those specific lists that we had, and also monitoring for stream processing by creating a practice of meaningful, iterative, and accessible metrics. So moving outwards, as for metrics for the other engineering teams around us, we knew that if everyone was looking at the same initial metrics, that no one would actually be getting the information that was useful to them, even if there are other engineers. So there had to be some sort of filtering or abstraction, but it really didn't need to be complicated. So most of this just revolved around a few additional basic data-driven concepts, including keeping our alerts small in modular units and using the language and tools of our intended audiences. In the end, we just ended up relabeling our alerts and monitoring with the tag for the specific team that it would impact, and using Slack integration for PagerDuty, Jenkins, etc., we just routed the alerts that pertained only to that specific team to a Slack channel that only had that team in it. We actually tried a lot of other things that were much more complicated and way more fun to program, but much less fun to use. So this ridiculously simple method scaled so much better than all of our other attempts, and it was actually able to keep up with that new complexity and any complexity that our downstream ecosystem came up with very minimal effort from us. I do want to give an example though, specifically for the added impact of upstream teams in the stream processing. So here's a slice from that earlier dashboard, or Kafka lag for each incoming system. So initially we were alerting on any spike in lag over a certain threshold. which the threshold we had selected because it made sense to us in the context of our data pipeline and based on the behavior of the majority of the streams we were consuming. However, although we have a great example of an abnormal spike here at 9:45 for 2 of the incoming streams in this example, so clearly that we definitely still needed that threshold, the spike in lag from 9:10 to 9:15 was actually normal for these streams. It actually would have been abnormal for the other streams that we were consuming, but because of how and when these particular ones published their data to us, this actually was their normal. So that was a pretty important thing for us to check with our alerting. A couple gotchas though. So when working around a predictable daily spike or drop, I've learned the hard way that particularly for upstream teams that use batch processing, that there needs to be a procedure to notify the teams along the rest of the stream if they decide to maybe change their collection or publishing schedule, because obviously that can have a pretty big impact. Or worse, autonomous teams don't always base their event time processing in the same time zone. So you could have a team using UTC and one, say, a time zone that maybe handles daylight savings time totally differently, like PST, and you could very suddenly be tracking or compensating for the wrong things. At best, you can get paid for something that's actually normal. At worst, your nice custom metrics are now working against you. So overall, this is an example where enabling metrics to continually guide how you measure and alert on your data, particularly around integration points for streaming, is so incredibly helpful, particularly for anyone that's going to be sharing that integration point. So I'm getting low on time, so I'm going to go through this one a little bit quickly. And basically here is an added challenge of abstraction and a group that typically wants to be able to pivot between depth and summary. So in speaking with people on both sides of this, both sides consistently emphasize the importance of using tools and language that are familiar to the target audience. As Noshnika Fee, a fellow developer advocate, said to me recently, the further you get from engineering, the more your status just needs to be a URL, but you'd be surprised at how far that gets you. And I gotta say, I've had a lot of success with that as well, particularly with something like a blog post with language that's catered to that audience, while embedding a few automatically updated charts or numbers into that post. So keeping it automated, but also keeping it in the language that works for them. So this part is the most abstracted from the topic here, and your metrics will likely have already been translated by a customer-facing professional at this point, so I'm not going to get into this one, but I do want to add it because I think it's important to include as a reminder that this is definitely still very much a part of your metrics picture. Okay, so with that, we've covered using metrics to drive your development process and how that looks different for stream processing, specifically keeping your metrics meaningful, iterative, and accessible. We've covered using metrics to minimize some of the human challenges that come with stream processing due to its unique impact on the rest of your technical ecosystem and integration points. Specifically, we talked about how to automate filtering and abstracting metrics in a way that work for different groups of people who share those integration points, and keeping it as simple as you can with techniques like small modular units and using the tools of your intended audience. And with that, thank you all so much for coming. And huge thank you to the DataEngBytes AU team. You've been amazing and really thrilled to get to be a part of this. Thank you also to everyone that helped out. Cheers.